Log on, tune in, find out. Another good idea from Cambridge.
Last talk in this session is from Andrei Bejan from the University of Cambridge.
Thank you, Andrew. Well, it's 5 p.m. and we're only one talk away from the conference dinner. And I just thought I'll take 1 minute of my time to make this point of relaxation of this regeneration process of talks and offer you a nice little problem, which I think some people, but only a few in the audience would know. They have heard it from me. Not more than 3, I think. So I only need a napkin to do that, and we can easily call that napkin problem. Your napkin should be a square, and we consider all foldings that contain its center. Yeah. So I need a folding, and we consider all such foldings. So they vary from half square, rectangle, to triangle, another half square. And the optimization problem is this: to maximize, find such a folding that maximizes the area of this shape. I'm collecting solutions. So doesn't have to do anything to my topic, to the talk, other than can also be considered, well, it's optimization problem, both in space and time. It's geometric optimization problem for you. It's optimization problem for me in time, because I need to choose carefully times when I will ask you, did you solve it? I will not want to ask you too often. And it also creates a graph in this little community with a star topology, where I happen to be the central node because I gave you the problem, and you happen to be the end nodes. Okay, so I would like to tell you about some parts of my PhD research which I did at Hertford University in Edinburgh, and this is a joint work with my supervisors, Gavin Gibson and Stan Zachary. Gavin will be giving a talk later this week, I think tomorrow. I've got a lot of slides. I'll have to make sure I go quickly through them, especially I'll go quicker through things we all know, but I decided to concentrate on as well. Okay, it's about Bayesian experimental design for percolation and random graph models. At the time I started my PhD, there was a feeling there was not enough attention for these discrete structures in terms of experimental design. So I will describe the model and I will discuss the optimality measures. Then, of course, I'll describe the model of optimal design for the random graphs we're considering. It will mostly be optimal arrangement problem for the nodes of the graph, where edges will be random. Then I will give you results that we know for basic random graphs, that will include proximity graphs, threshold graphs, and some general results for sequence of graphs, worst case scenarios, where configurations grow, indefinitely grow or diminish. And then I'll go to percolation models, where we have connections to plant epidemiology and epidemics in structured populations, and I'll conclude with identifying some future work. Okay, so assume we have a set of X of potential nodes for our random graph. We consider, so we assume that for each node there is a weight, R, U, V, and we consider an arrangement of n objects within this region of n nodes. N is fixed here. We assume that between each pair there is a link, and that link is established according to so-called edge probability function, which is a function of the weight. And of course, it is natural to sometimes to assume that these weights might stem from a metric, and we may additionally require some conditions, and natural ones are this function is 1 at 0 and 0 at infinity. Okay, so X can be continuum, it can also be discrete, and also there will be some topology structure of interactions given. So in the case of square grid, there might be 4 nearest neighbor interaction, there might be 8 nearest neighbor interaction, there might be long range interaction. So examples of the edge probability functions. Linear decay, well, clear it cannot decay indefinitely. There will be decay to 0 and then, to some level theta, and then probability will be 0. Exponential decay, power, Cauchy decay, threshold, and threshold is so it's a profile where links always appear if distance does not exceed a certain level, and then they only appear with some probability alpha, where alpha might well be 0, and then you have proximity graph. Logistic kernel here as well. Okay, functions 1 to 4 satisfy monotonicity conditions that we listed before, and what else? That's it. Let's go further. So to summarize, we have a model, and the model, the statistical approach is this. We believe that our graph will be governed by a function p r theta, where p is a function from a family of functions. So quite often researchers will study phenomena that will lead to such models, and researchers will have good grounds to assume this decay function has a certain functional form, but what will not be known is the rate of decay, parameters that specify function from this family. And theta is statistical parameter here. Our statistical interest is in making inference on theta, and the design question is how do we choose these n nodes within a set of potential nodes to observe a realization of the random graph, so that our inference on the model parameters is most informative. And that, of course, has to be measured first. And the motivation is this. Well, basically, any phenomena that lead you to such graphs where link appear randomly. But look at this, n operating devices with random lifetimes. At which time moments should one check their status? Well, you might be thinking now, what does it have to do with graphs at all? This is a temporal problem. Well, I'll show you just in a minute that yes, it is a temporal optimization problem, but I can consider a star graph there. So the point is this: we can reduce quite a lot to graphs, to these discrete structures with different topologies. Well, more to the point, radio networks where we have successful, unsuccessful connections, and that will depend on the properties of nodes as transmitters or receivers, and also possibly on the medium within which they operate, and also on the distance. Again, temporal processes, aging and fatigue processes, where are graphs there? Well, the response again can be transformed into binary response, and in psychological experiments or neurophysiological experiments, it can be binary response to stimulus applied, or we have probability of retention that obviously decays with stress put on agents. Disease evolution on networks, and that's probably the most motivating scenario for us. Let me just show you this figure, which is a reproduction from a work of Bailey, Otten, Bailey not Rosemary, Otten and Gilligan, which shows how these people who have interest in plant epidemiology model a spread of a disease of a fungal pathogen in soil medium from plants, from plant to plant. And in this particular paper, modeled it as a percolation process, and they distinguished, as well, I think, long percolation process, and they distinguished between invasive behavior of the fungus and non-invasive behavior. So similarities to percolation process on lattices, and that's what they would typically do in the laboratory. They would, of course, need to come up with a good structure of the lattice to run process and make inference on the parameters, the model they are using. In case you're wondering what is saprotrophic there, it's a quality of ability of these organisms, typically fungus, to feed on decaying organic matter and take all that stuff through the mycelium to the ants, and that's how it grows. Okay, and to say this, so the model, I would approach this in this way, that variations are possible. Yeah, in what sense? The number of nodes doesn't have to be fixed, but we might just restrict the region within which we take the nodes. The design might not consist in choosing the nodes, but transforming the topology of the network or its shape. Observations can be incomplete. So the growth of the fungus is in soil, and practically you might not be able to see the edges of your network. Well, of course, we're dealing with a graph snapshot here, and ideally we should be dealing with a series of snapshots, so in the temporal dynamic. From locally d-optimal, so I'm starting to discuss optimality, and first there's a standard rant on d-optimality. For example, we have 3 nodes, let them be in the plane, assume exponential decay between points. This is the Fisher information function in this case. What is the optimal design? Your question, sorry, your answer to this question is, what's your feeling? How should I arrange these 3 nodes so that if I use Fisher information function, I'm most informative? Of course, there will be dependence on theta. So we have a Fisher information function is additive, and we assume independent nodes, right? Assume we have a relaxed problem. We don't have restriction of the plane or space. Now, of course, each of these terms can be maximized. There is a single maximum, and then the unilateral equilateral triangle still satisfies that. So the optimal design here is equilateral triangle. In case of 4 nodes, optimal design will be, and I know that from numerical work, I've not been able to show that analytically, will be a square. So symmetric regular design. Something that I'm personally not happy with. Just slightly more general example, we have n systems, they operate in parallel, their lifetimes are exponential, some decay, and what are optimal observational times? It's the same distribution, but they're independent. How should you sample each? When should you approach each of the devices? Well, again, Fisher information function, the same argument, there should be only one point when you should sample all the devices. Of course, the greater n is, the more information you get here, of course. Still, it is very strange, and that doesn't only apply for the exponential decay, you can change it. It's feels a little bit wrong, it should be 1 point. D-optimal designs require good knowledge of the parameter, and as William Cochran put it in 1973, you tell me the value of theta, and I'm going to devise a good, the best experiment for estimating theta. That's all what we all know. As I've just mentioned, there's symmetry or regularity, especially in spatial D-optimal designs. But of course, things can be tweaked, suited to Bayesian approach, and it is well known the optimal designs are not invariant on the general model reparameterization. But in 97, Firth and Hinde, and please correct me if things were discussed earlier, but they discussed and suggested to maximize this quality where we integrate out dependence on theta, and we also achieve invariance to the choice of parameterization. This is pseudo-Bayesian design, something that has been mentioned already before. Or we just choose some linear functional of I and employ Bayesian approach. Again, integrate out dependence on theta. Okay. Now, I would like to adopt utility-based Bayesian design. So for each particular observation and true value of the model parameter, I should be able to say what's the use of it for me, how much utility. And therefore I'm considering utility function, which is a function of the design itself, the model parameter and particular observation. Then when they vary, they're random variables, this is a random variable. Possible choices, well, we might want to minimize the squared difference from the posterior mean to the true value of the model parameter. We may act in the Bayesian setting and minimize the precision in the Bayesian sense, which might be variance. From some considerations, we might want to increase or minimize the total number of observed edges. Okay, and another possibility for the utility will be log of the ratio of posterior to prior. And that, if we want to maximize the expected utility, something that we'll be doing, that corresponds exactly to the use of Kullback-Leibler divergence or Lindley informational measure. And this is our setup, optimal design as an optimization problem, so where after d star, which maximizes expected utility, this integral in the joint space of y and theta. Okay, of course, this is our model of likelihood function. Okay, I've got to be really quick here. What are ways of maximizing expected utility? Well, from analytical to numerical or some tricky ways, MCMC. In fact, I'll be in the results. I'll show you we used. I'll have toy models and proximity models where analytical evaluation is possible, and I'll show you a percolation problem where we used combined analytical evaluation after sampling and fitting a distribution, so a mixture is possible. And I also made use of Müller's approach of defining an artificial distribution. So here we need to maximize this quantity. Now, if we define a distribution which is proportional to this guy, and then if we're able to sample from it, then taking marginal in D will give you the optimal D, the mode of marginal of our augmented distribution H will indicate where the mode is. Also, of course, there are questions of unimodality and multimodality of the expected utility we encounter here. I think I'll skip this. The whole idea is this, that in this utility-based Bayesian approach, where our utility is log of the posterior to the prior, that is nothing but the expected Kullback-Leibler divergence of the prior to the posterior. And that coincides with the expected Lindley information measure, where Lindley said, okay, well, we have Shannon entropy, then we have entropy of the prior distribution, we have entropy of the posterior distribution, let's take the difference, but then the difference will depend on the observation, or we need to devise design before we will observe, actually take the expected value. So these things coincide. Phi here is marginal likelihood prior predictive distribution for y. We'll encounter it later. That's what I've just said, this relationship between Shannon entropy, Lindley information measure, and Kullback-Leibler divergence. Now, I found useful to have these two lemmas to prove some results. The first lemma gives another form to the expected utility, to the expected Kullback-Leibler divergence, and expresses it in the form, in terms of entropy of the prior predictive distribution and expected entropy of y given theta. And another lemma tells you how to differentiate entropy of a function with respect to the parameter. So of a density with respect to the parameter. Now, first, a result which I will not be using in practical problems, but I found striking that the first paper where this result is encountered, well, at least I didn't find any earlier papers, is in '94 by Parmigiani and Berry, and this gives you sort of this gives you a way of differentiating the expected utility under the integral. Not of much practical use, of course, but still they're trying to use it even for discrete d. Of course, you need to have continuous d, but maybe explanation is that it's not of much, not much of practical use, but still quite interesting that you can do this change of, yeah, you can differentiate under the integral in this nice way. So two lemmas are used in order to give an sort of, well, almost essentially the same proof, but alternative proof of this theorem. Now this theorem has to do with graphs. Now we've chosen the measure, expected Kullback-Leibler divergence, and assume that our node configurations are such that all the distances diminish or grow indefinitely, uniformly. So if I take the minimal distance and let it grow, or maximal distance and let it diminish. So of course we would encounter more and more situations where there are either no edges or all edges present. And that will be the least informative scenario. The question is it really the case with choosing this measure? So this theorem says that it is the case. If you have a sequence of graphs with bounded node degrees, is it correct? Then expected Kullback-Leibler divergence tends to 0. And also we all know that if we deal with Kullback-Leibler divergence, we have the term entropy of the prior distribution that doesn't depend on the distance. Now I also find it useful actually not to forget about that term, even if I'm not dealing with it when I'm maximizing expected utility. Why? Because if you do things, if you do some numerics calculations, then that might be a way of checking whether you did things right. Because when you have worst case scenario, your expected utility will approach that asymptote. Yeah? And it's prior, you know it, and you can calculate the entropy. And this is a toy example where you have just two nodes, exponential decay, nice analytical evaluation, in fact shows you that optimal design just scales, and you can just maximize this function W alpha D, and just to show you that indeed, you know, D is increasing and it approaches the minus entropy of the prior distribution. Okay, and this is to show you that everything is possible for the expected utilities for such graphs. Flat surfaces, more flat surfaces, everything is possible. Proximity graphs. So there is an edge if the distance between two nodes does not exceed a certain threshold. So what you will not know is that threshold, and you would like to arrange the nodes so that you make most informative inference on that. Again, we have an analytical result for this, for the proximity graph that says this. So if you have no additional planar so spatial restrictions on the distances, and so you can think equivalently of a star-shaped graph, then the solution to the n-node optimal design for proximity graph and the star topology is given by n-1 quantiles of the prior distribution. So all you need to know is to split prior distribution in n-1 equal parts, on n equal parts, and take the quantiles. And the proof is quite straightforward, simple, and there is an example here where you have red lines are quantiles of pi theta, so for this scenario with relaxed conditions. And you may ask, well, okay, what if you are in the space? We know what to maximize. So in this theorem, we actually know what to maximize. Just add the constraints, and that will work fine if you do some numerics. So I applied genetic algorithm, and that seemed to work well, just for configurations that are restricted to the space. For threshold graphs, where we have alpha threshold, things are also possible to devise analytically, and I'll just go further. Percolation, very interesting topic, and I'm almost out of time. Now, percolation is well known. Who doesn't know, who never heard about percolation? Mathematical percolation, of course. So, okay. Percolation is a process of, so we have a network or we have a graph and we claim a link open or closed with certain probability. So, and then we are wondering about such questions as, is there indefinite cluster? What's the probability of the origin to be an indefinite cluster? Or, of course, about probabilities of all sorts. And central to percolation is this concept of criticality, where if you're wondering about what's the probability that the origin will be in the indefinite cluster, then up to some point, so for P, for the bond percolation parameter with which you claim the bond is open or closed, up to some point that probability is 0, and there is a critical level at which it is not 0 anymore. So this, when you pour water into coffee, it is not dropping yet up to some point, and then it percolates suddenly. Now we use percolation to because there is a connection between an SIR epidemic with constant lifetimes, infectious times of sick plants. And yeah, percolation, we use this connection, and we do mean SIR epidemic, but we talk about percolation. And the connection is this. So if we have an SIR epidemic with fixed infectious times, then the epidemic can probabilistically be realized as an unoriented bond percolation process. In what sense? The distribution of the set of ever infected nodes or sites just coincides with the distribution of sites from a cluster in the corresponding percolation model. Now, so you can think of percolation as a model which we use for the spread of fungus, for example, where we only restrict ourselves to the nearest neighbor interaction. And we also consider that we have incomplete observations. So first scenario is that we don't observe the edges, and second scenario, even more incomplete observations, where the only thing we know is the size of the cluster. This scenario, so for this second scenario we have some theoretical results for the MLE of the bond percolation parameter. Not much use in practice, but let me show what we have for the first scenario. So we make inference, and the design problem here is how to arrange nodes optimally. So to do the design problem, I need to be able to make inference, and I make inference using MCMC. Expected utility involves posterior, and I used to evaluate, I use the Muller's approach of augmented probability modeling. So I run MCMC to sample to find the mode of U, and in each evaluation I'll need to evaluate the posterior. So it's an MCMC within MCMC. Now, this is just a plot showing a result of producing a sample for the posterior, and the line here is for the complete observations, including edges, so just likelihood. These profiles are smooth versions of the histograms from MCMC for the second scenario, where we only know the eventual size of the epidemic. I have little videos that I will probably show at the very end, maybe if there is some time, that actually I have a perfect opportunity actually to visualize what's going on mathematically. In fact, I should have been describing MCMC and all that algorithm, but in fact all I need to do is to say, well, my MCMC explores the joint space for P, of course, and the set of all connected components on n nodes. That's for the second scenario, or the set of all connected components that correspond, that also contain the origin. And how does it export that state? I have nice illustrations, videos to show you. And if I don't manage to do it now, you can always ask me. They'll be available online. Okay. Now, in order to devise designs, and we identify so-called inner-outer plots. And the idea of introducing inner-outer plots is this. So we'll have a bounded region, let's say a square, and we'll consider that square and also squares which are obtained by sparsification, by removal of some nodes. So infection will not be able to travel through those nodes. So you see, we use this, we'll use a complete plot from the underlying lattice, and we'll also sparsify. And we'll say, okay, let's consider this family of plots where we have sparsified plots. So we show, using all these techniques, utility-based approach and MCMC, that actually considering mostly packed configuration as an underlying topology is not always optimal. Sometimes you need to sparsify. And maybe just, oh, I think I pressed something. Okay, I'm able to do this. And the final maybe picture which explains things. So my family now of design plots is very simple. It only contains 3 plots. On the plot C, we didn't remove anything, but that's just bounded part of Z2. On B, we removed sides from one of the outer circles, and we sparsified even more. And then you can see 2 figures here. Let's concentrate on the figure from left and ignore figure on the right because it corresponds to the to a scenario that I didn't describe. So in the figure in the left, we see actually a histogram for the marginal of the augmented density of that H, which is proportional to the integrand from the expected utility. And that says that B is more optimal than C, and this is for the scenario where we will not be able to see the edges, where the only thing that we see is the set of ultimately infected nodes. And C is more optimal than A. Okay. Should be finishing. And I am. Of course, in percolation process, we only considered constant infectious times. Non-constant infectious times will lead to so it will be important how those ordered edges were formed in time. So that process will have to be taken into account. In principle, the methodology can be extended. I cannot say how much and what will be the complexity of calculations in terms of MCMC. It's always an art to come up with a good sample. The design can be considered in terms of the optimal lattice shapes. There is some work in my thesis as well. We assume, again, as it was said many times, we assume this model. We believe it holds this family of distributions. But model robustness issues and misspecification of the models or designing model choice experiments would be good, especially for graphs, would be a good thing to do. Of course, temporal graphs evolving in time or sequence of snapshots will be a good thing to do, and you might have your suggestions. Sorry, it was a lot of stuff in half an hour. But there is a paper and there is my thesis, and thank you for your attention.
this scenario where you said with the soil, we took tests from soil to, I think you tried to identify the topology of the network in the fungus. That would be the
To
problem.
characterize the topology of the. So I don't know. Maybe Gavin would know better because he certainly communicated better to Chris Gilligan.
Well, the picture that you showed of the experiments,
Yeah.
these are actually agar gel spots. So they're kind of artificial experiments. So you have freedom to assign where you put the agar gel spots. The pictures you showed was a particular configuration that they were using.
Yeah. So the question was, when this fungus grows, is there a good characterization of the network topology in soil that it creates?
Of the actual mycelium,
Yeah.
most of the pictures they have are in 2 dimensions because it's the fungus growing on the agar. Okay, so I don't know what they have in terms of images of what the 3-dimensional topology would be. So it's slightly artificial, but 2-dimensional case.
Yeah, of course, there are a lot of simplifications here, but you need to start with something else. An obvious excuse always.
Okay, in that case, we'll bring this session to a close.
Yeah, the napkin problem, don't forget that.